In the previous video, we saw some interesting application of mod 2 degree. Well, interesting to me at least. I don't really know your preference. Now we'll go up one level. Here is the climax that we have been advertising, 1/2 of the fundamental theorem of algebra. We'll prove the fundamental theorem of algebra for the case of polynomial of odd degree. We'll show that complex polynomial of odd degree always have a root. By our previous discussion about the relationship between the degree mod 2 and existence of 0, we know that it suffices to just show that the degree mod 2 of this quotient is not 0. I'm being a bit sloppy here because I haven't told you the domain of this map yet. We're gonna do that later, but no matter where the domain of this map is, if this degree mod 2 is not 0, then P will indeed have a 0 on C. Now, to show that this degree mod 2 is not 0, it suffices to show that this degree mod 2 is going to be congruent to degree of P, modulo 2. And that's why we added the assumption that degree of P is odd. Let's call this degree of P D. Then the idea of the proof would be as follows. We will construct a homotopy between these two maps, the power map z to the d and this quotient map. Now, because this degree mod 2 was defined in terms of intersection number mod 2s and intersection numbers mod 2 are homotopy invariant, so then from the fact that these are homotopic, we deduce that the degree mod 2 of this map is going to be equal to the degree mod 2 of this map, which is just going to be d mod 2. How do we know this? Well, we can just do that by counting points in fibers over regular values. Every non-zero point is a regular value of this map, and every such point has exactly d preimages, the dth roots of it. Alright, so now let's construct this homotopy. This family of maps is going to be given as follows. First, we construct this homotopy. You can think of this as a straight line homotopy between pz and z to the d. If we fix the point z0, then as t runs from 0 to 1, the value of pt z0 runs from here to here, along this line segment. Then we can choose a really big ball B, so that none of these map pt have zeros on this boundary of B. In particular, these quotients are well-defined map on the boundary of B, and thus gives us a homotopy between this quotient and z to the d. Now the last question we need to answer is, how do we know we can find such a ball B? Well, the idea is that as z goes to infinity, this quotient gets close to 1. So if we take a ball with radius big enough, so that z is really big, then this quotient is not going to vanish. And in particular, this numerator, pt, cannot vanish. Thus, for a large enough ball, these quotients define a family of maps from the boundary of B to S1. This gives a homotopy between this quotient and z to the d. So then, as degree mod 2 is a homotopy invariant, we know that these two degrees must be the same. So in particular, the degree mod 2 of this quotient must be equal to the degree of the polynomial p, which is odd. By our previous result, this means that P does indeed have a root in C. Isn't it incredible? From something as coarse as this mod 2 degree, we can actually get such a powerful result. However, it would indeed be nice to have a little less crude, more nuanced invariant. So next, we are gonna talk about another alternative. Instead of intersection theory mod 2, we are gonna talk about oriented intersection theory.